In this video, I'm going to introduce the topic of acceleration and link that to when we did constant velocity motion by starting with going back to a position versus clock reading graph for an object in motion. So here below the data table, I've got a picture of a ball rolling down a ramp that is 128 meters long. It's a rather long ramp. And I have made up some position and clock reading data showing where the ball is on the ramp as time passes. So at 0 seconds, the ball is at the top of the ramp. 1 second later, the ball is 2 meters from where it started, so on and so forth. And by the time we get to 8 seconds, the ball is at the bottom of the ramp. And over here on the right, I have a position versus clock reading graph that graphs the data shown to the left. Now, when we did position and clock reading data previously, we had buggies that were moving at a constant velocity. And so what your data looked like then was that it was actually linear. So if you recall, when we did that experiment, the data looked something like this, where we had a straight line and the position changed by the same amount every time. So 2 seconds changed by 20 meters. Go over 2 seconds again, it goes from 20 to 40, so a change of 20. Go 2 seconds again, from 40 to 60, so on and so forth. So that represented constant velocity because the position changes by the same amount every time. What makes this different is that the position does not change by the same amount every time. So if you look over here, after the clock ticks by 1, the position changes by 2. And so we see from this data point to this data point, there's not much of a difference in the position. Okay. Now when the clock ticks again, the position increases by 6. So from this tick to that tick, we had a change of 2. Okay. Now when we go from 2 to 8, that was a change of 6. Now when we go from clock reading 2 to clock reading 3, from 8 to 18, we get a change of 10. And just to keep going, we go from clock ticking 3 to clock ticking 4, goes 18 to 32, which is 14. So we can see, that's kind of an ugly 4, so we can see that the change in position gets bigger. Goes from 0 to 2, and then 2 to 8, which is a change of 6. Goes from 8 to 18, which is a change of 10. And then 18 to 32, which is a change of 14. And if we keep going, you can see that the change in position gets bigger. Instead of just going up 20 or up 10 each second, the change in position gets bigger. And so that's why we don't see a linear graph here. We see something that's not linear. And so one other way to look at this is that if I track the position for each data point, we see that right here, there's not, I mean, it barely goes up a little bit. The position barely changes. Okay? But if I look over here, it's still a small change. I mean, it's just that width right there, but it's definitely bigger than the almost barely change from the first data point to the second data point. And so if I keep looking at the changes, okay, go from here to there, that's another jump. Okay. And then as we go to different data points, you can see that, at least see it visually, that the jumps from one position to the next get bigger. So, and we'll do the last one here. And so let me change colors here, and can see that from this jump to that jump, that's barely there. It's just a little bit. And if I go from here to here, okay, that's like going from this clock or this position to this position. The jump is a little bigger, not much, but definitely bigger. And as I keep going, these jumps get bigger and bigger and bigger. And so that's what it means for something to accelerate in physics, is that the spacing between positions changes. And when the spacing in positions gets bigger, we'd say that the object is speeding up. And one way we can represent this is to go back to motion maps. So previously when we did a motion map, that was when objects all had constant velocity. So we would space the dots the same distance apart. We would draw the arrows the same length, kind of trying to do that here. And so we represented constant velocity by showing the jump between each dot being the same, or I tried to draw that the same, and also the arrow lengths staying roughly the same, to show a position that changes by the same amount every time. Now, if we want to do this, show a motion map for an object speeding up, we have to show the position changes getting gradually bigger, like it does in the data table. So to show a motion map for an object speeding up, we'll start here, show that it starts at rest. Okay. We'll make the first position change. Okay. I'm going to give that a little arrow because it's not moving very fast. Now, the next position change needs to be bigger. So the next position change needs to be further apart than from that first dot to the second dot. So I'm just going to make that a bigger position change. Okay? And then I also need to draw my arrow a little bigger. Okay? And so we can see that the position change from the second dot to the third dot is bigger than the position change from the first to the second. And so that trend needs to continue. So I did 1, 2 spaces here, so I'm just going to do 1, 2, 3, 4. Okay. Now it doesn't matter for a motion map exactly how you space it out. As long as the arrows are getting longer and the spacing is changing, that's all that really matters. Okay. So this video was made just to get you used to the idea of thinking about speeding up in terms of what happens to the change in position of an object while it's speeding up. Now, slowing down is a different matter that we'll look at later. But for now, just the thing that I want you to take away from this is the difference between constant velocity and changing velocity in terms of position is how the position changes. So in constant velocity, the position change is the same every second, but for speeding up, the position change gets bigger. So our jumps between locations get bigger. So there's that jump, the next jump is bigger than the previous one, the next jump is even bigger, and we could keep going and going and going and showing its speed up.